second scene.
Perfect. So it's a pleasure to be here today and to share you more about battery, what we are doing, but also a bit about the history, what led to the incorporation of battery, and what work have we been doing at Empa beforehand, and what are our future plans. Before I start, I would like to acknowledge the team. I'm presenting here today, but this is work, of course, of a larger team. Here you see the whole team members, and the company was founded by Jaroslav, Abi, and myself in 1.5 years ago, roughly, a bit more than 1.5 years ago, in April last year. And the three of us, we actually have been working together for quite a while. We have been sitting even in the same office. Jaroslav was a group leader back then. Now he's a laboratory head at Empa. Abi was a PhD student in the group, and I was a postdoc and scientist in the group. Since then, the team has grown quite a bit. Nico joined our company yesterday. He was also working at Empa before. Miguel is already with us for quite a while. He was in a different startup beforehand. He's now working as a quality engineer in battery. Xinyao, a battery engineer who has also been working with us from Empa. And Tudor is a process engineer at Empa, which works together with us through a funding from Gabriel Foundation. We also have Gero, who works on business development, who has previous consultancy experience, and Laura, who helps us on everything communication related. We are a spin-off of Empa and ETHZ Zurich, as mentioned before, and we have many partners and supporters, as all seen here on the top. And we have advisors. One of them is a battery expert, will be announced very soon. He is a successful founder of a successful German battery producing company. He recently is not operational anymore and supports us now as an advisor. Tilman from Anybotics on marketing. Bettina is an InnoSwiss coach with experience in private equity, and of course, Jaroslav. So what do we do at Battery? We working on batteries at Empa. We've seen that there are different energy storing technologies. First of all, you have lithium-ion batteries. They are very good in storing a lot of energy, which has allowed for the electrification of cars and buses, for example. And then on the other hand, we have supercapacitors. They are very good, and if you need very high power pulses, so they have very high rate performance, but they have little energy. But there is no technical solution which can combine both energy and rate in the same device. And this is what we are working on. We are working on a technology which can combine both energy and rate in the same device. And we are doing this by using advanced semiconductor fabrication methods. So our batteries are fully produced using semiconductor fabrication methods. And this allows us to build a battery which has very high C rates, so up to 60 C, charging and discharging in just 1 minute. They can be made ultra thin, so just below 0.1 millimeter in thickness, and they have a low self-discharge rate of about 1% per year. And directly starting with what is our vision, what do we want to achieve? Our vision is that to fabricate a battery which can combine this charging time of 1 minute with high energy densities of today's lithium-ion batteries. And how is this possible? This is really possible by semiconductor fabrication methods, having very thin layers and stacking them on top of each other. And I will go into detail a bit later on. We also envision a more stable temperature operation from negative to positive, because it's all solid layers. There's no liquid anywhere hidden. And the materials which we're using, they have been proven to cycle for 10 times longer compared to today's lithium-ion batteries. Before I go a bit more into depth, I would like to quickly look at the evolution of lithium-ion batteries. So here you see the generation 1 to generation 4, and some ideas what have changed over the years. There's been a lot of progress starting from the generation 1 batteries, where we had graphite as an anode, liquid electrolyte, and cathode, something like lithium cobalt oxide. There's been a lot of work from both academia and industry to improve these, for example, by using different cathode materials, for example, like nickel-rich NMC materials, but also changing on the anode, the chemistry, for example, adding silicon into the graphite anode, And there are now first companies who bring pure silicon anodes into the market. And then we, of course, have the solid-state batteries, where the difference is now we don't have a liquid electrolyte anymore, but we have a solid-state electrolyte, which also acts as a separator between lithium anode and cathode. And here this allows us to for example, also use different material combinations, such as lithium metal anodes. And that there has been a lot of progress and a lot of improvements over these devices. But one thing really remained very similar throughout the years, and this is the structure of the battery. So all of these layers, for example, the cathode, they are typically in the order of 100 of micrometers in thickness. And the thickness of the cathode is one of the aspects which really limits the rate performance of these devices. And here you can again see this in a different schematic way, where you have a solid-state battery, where you see also the cathode is actually not a pure material. This is, of course, a composite material with the active particles, but also some additives for conductivity. And this is under development, but as mentioned, these are rather thick layers still, which limits the rate performance. Thin film batteries is another type of solid-state battery, and it's actually the only commercialized solid-state battery today. There has been many, today, and they are different that they are very thin. So the material is typically in a tenth in the thickness compared to solid-state batteries. So you often see cathodes in the order of just 1 micrometer thickness or a bit higher. And because the cathodes can be so thin, just 1 micrometer, they can be charged and discharged very quickly. So we have very high rate performance with these materials. However, we typically have them on a substrate. So in the substrate, in research, this is even sometimes silicon wafers. They're very bulky. In industry, this is more thin metal foils. But still, these metal foils, they're typically in the order of 10 micrometers thick. And now if you assume you have 10 micrometer thick of a foil, and a very thin cathode on top of just 1/10 of the thickness, this is a poor energy density. And what we have been working on and what our vision is based on is really to now combine the benefits of both. So to increase the amount of cathode per substrate while not losing the high rate performance of these thin film batteries. And we can do this by stacking several of these thin film batteries on top of each other, on top of the same substrate. This means basically that we reduce the weight component of the substrate, and by each cell we are reducing the total weight component of the substrate. And doing this allows us really to combine high energy and high rate. And there's one key difference between thin film batteries and solid state batteries or other lithium-ion batteries is the way they are fabricated. Thin film batteries really rely on vacuum coating techniques. And this is, sorry, there was one slide in between. Let's jump to the vacuum coating techniques first. Vacuum coating techniques. And this is really a method. It's a proven, scalable process, which is often used for high quality filmers and also if you need precise control over the thickness of the films. This is methods which are used in different industries. For example, in the OLED industry, typically OLEDs are mainly done using vacuum coating techniques. And there has been even 10 years of research, both of academia and industry, to replace these vacuum coating techniques with liquid coating techniques. But still today, OLEDs are made with vacuum coating techniques. This is also a technique which is used in solar cells, for example, but also in semiconductors. And the benefit for these techniques is, as mentioned already, they can offer very high quality and precise control. They can also be very highly automated in fabrication systems, which make them attractive to build a factory even in places like Switzerland, where labor is typically expensive. So you can envision such a factory standing in Switzerland as long as it's fully automated. As one example, we are typically looking at is, for example, Swatch. Swatch is able to produce their full watches in Switzerland because they're fully optimized. And also, vacuum coating is something where Switzerland is strong, Switzerland and Europe, where we have a lot of expertise, a lot of companies working on vacuum coating techniques. Now, to this slide, I wanted to mention that thin film batteries are nothing new. They are around since a while, since the late 60s, where the first primary thin film cell was reported, where the primary was reported. In the early 80s, then the first secondary rechargeable lithium thin film cell was reported, with titanium disulfide as a cathode and lithium metal as an anode. And then it really the field really started to take on speed with the discovery of LiPon as a solid state electrolyte, and this is still the most widely used solid state electrolyte within thin film batteries. And the discovery of LiPon led to the commercialization of many of these thin film batteries, especially in the year 2000, 2010. There were many companies around the globe who tried to commercialize thin film batteries. Most of them are not around anymore, with the exception of two, which have been bought successfully in the way. One was bought by Apple, and one was bought by Dyson. And then another milestone and important fabrication to mention is here also by the Oak Ridge National Laboratory, the same who also developed and developed this solid state electrolyte. They showed that they could successfully cycle for more than 10,000 cycles, and still after 10,000 cycles having a capacity of 90% from the original capacity. So in this part of the talk now, I first want to highlight some contributions which we have been working on at Empa in the laboratory of thin films and photovoltaics to really bring some additional improvements to this thin film battery field. And I especially want to highlight three different works. One was how we reduced the amount of cobalt by switching the cathode from an LCO to an MC811 cathode. How we were able to reduce the amount of lithium by developing an anode-free thin film solid-state battery. And then how we can increase the energy density by stacking these thin film cells on top of each other. And the work from Empa was funded by different funding agencies, which I mentioned here below. So let's look first at the NMC811 cathode. This is work which was developed by Abdeselem Maribia, one of the co-founders of the company, now the CTO, who developed processes for NMC811 as a cathode. And as far as I know, we are still the only one which can fabricate these materials and these cathodes in a thin film form factor. And here you can see the performance of these thin film cathodes in liquid electrolytes. Typically, and what you see is basically if you have the standard voltage range from 3 to 4.3 volts. As soon as you change this either to high voltages, you have very strong degradation, or to low voltages, you also have very strong degradations. This is very different if we have the same cathode now in a solid-state electrolyte. If we use a solid-state electrolyte, first of all, we see that the cycling is much more stable, but also we can access a more wide voltage range. So we can here, he showed that he can cycle from 1.5 up to 4.7 volts. And this is really only possible with the use of this LiPon solid-state electrolyte. And he even showed that he could cycle this for 1,000 cycles here with a cycle life of 900 cycles when it reached below 80% of capacity. Then another topic, which is the anode-free design. This is also a topic which is often addressed in bulk solid-state batteries. So why do we want an anode-free design? First of all, having lithium metal anode in the fabrication process complicates things quite a lot, because lithium metal is very difficult to treat and to handle and to fabricate, and it needs very clean environments. And on top of that, ideally, you would have very little excess lithium metal into your batteries. So one way to do this is to fabricate it in anode-free design, which means that there's no anode present in the fabrication. So you only fabricate a cathode, a solid-state electrolyte, and then directly the current collector on top. And this is more or less what is highlighted here. So you see the copper on the bottom, and then there is a small interlayer, in this case carbon, and then the solid-state electrolyte LiPon. And this now represents the anode side of the cell, where there would be no anode present, just a carbon interlayer. And the work here was really on focusing on this interface and to develop a material which allows for stable plating and stripping of lithium metal. And in this case, this was a carbon interlayer right here. And what we could show is that we can now very homogeneously plate this lithium metal. So what you see here in the middle graph, where we really from the top apply the current and grow this lithium metal. And you can see this is very homogeneous by looking, for example, at the features on the bottom of the copper. They're all still present on top. So there's a really homogeneous growth. And this is done at room temperature and without any applying any pressure. And of course, we can remove the lithium again by stripping it, and then the lithium is completely gone here. And this now allows us to build an anode-free thin film solid-state battery. And in the publication, we even showed that we can do this up to current densities up to 8 milliamps per square centimeter without leading to short circuits. And here you can see one example where we now combine both of these concepts. So this is now an anode-free thin film battery with an NMC 811 as a cathode. And you see that that works relatively well. We have very stable cycling performance here and with reasonable C rates. And this was actually one of the first measurements which I've done together with Abi when I joined Empa a few years back. And then we really looked into all of these concepts in more detail. Now to the stacking. So far we only looked at single thin film batteries, where we worked on the cathode and the anode. And now you still have the problem of the substrate. So we would like to stack these cells on top of each other. And we had this in our heads for quite a while. And then we at some point hired a student to really build this proof of concept of this stacked thin film battery. And it was Luc Brinkmann, who was with us for 8 months, and to demonstrate that the stacking is possible and feasible. And this you can see here. On the right-hand side, you see a photograph of these cells. They are very tiny. So they are 1 by 3 millimeters in size. And you see that there are different contact designs, such that we can contact the bottom cell alone and also the top cell alone, but also we can contact them together. And on the left side, you see a cross-section of an SEM image of both of these cells stacked on top of each other. In this case, we now have LCO as a cathode. This is even an amorphous LCO cathode. This is not the best cathode at all, but this was really just for demonstrating the proof of concept. We have the LiPon as a solid-state electrolyte. In this case, silicon as an anode and copper as a current collector. And then repeat this again to really have the second cell on top of each other. And here you already see why vacuum coating is important here. We have here quite a lot of layers on top of each other. And these layers are very thin. So we need really high precision fabrication methods to enable several cells on top of each other with a high yield. And here you see the performance of these cells, where you see in green and blue, you see what happens if we cycle these cells individual from each other. And then if we cycle them together, we see that the voltage doubles, as we would expect if we electrically connect such cells in series with each other. So this means that also the energy has doubled of this cell without additional substrate contributions. So now what is the potential of such stacked thin film batteries? We also did a model. This is a thermoelectric model where we calculated what are the limits of this cell design, how thick does the cathode need to be, and what specific energies and specific cores can potentially be reached. Here we use NMC 811 as a cathode material, and we assume that 10 of these thin film cells stacked on top of each other. In addition, we assume a critical current density of 5 milliamps per square centimeter for the solid-state electrolyte, and a maximum heat generation of a heat difference of 100 Kelvin. And this basically defines this area here. And then you see here these lines, and these lines correspond to different cathode thicknesses. And you can see that if we go to very thin cathode thicknesses, we actually reach very high specific power densities in the order of 10,000 of watt per kilogram. If you take this to compare to a classic lithium-ion battery, this is about a factor of 10 higher than what a lithium-ion battery can offer. But we can still offer this at a very high specific energy density as well. You see that we are still in the orders of hundreds of watt-hours per kilogram. And this is especially true if we use very thin cathodes. If we use thick cathodes, of course, we are going into the regime of classical lithium-ion batteries, but also solid-state batteries. And here you can also see the C rates corresponding to that in green. And here you can see that, especially if we now look at the most part here is below 6 minutes, so above 10 C in C rate. And in green here, you see the line for 1 minute as well. And indeed, it's possible to fabricate a battery which can be charged in 1 minute, still having a high specific energy and specific power. So this is all what we have been doing in the lab at Empa. Now I'm switching a bit to what we've been working on at the spin-off battery. You've seen before the sizes of these cells which we have fabricated in the lab. They're very tiny. They're 1 by 3 millimeters in size, so 3 square millimeter. This is of course not useful for practical applications. So one thing what we have been working on a lot is scaling this technology. And here you can see this on the roadmap roughly how this looks. And end of last year, beginning of this year, we had cells which were 10 by 10 centimeters in size, which is also the largest what we can fabricate with the machines available at Empa. And this means that from those tiny cells to the large cells, we increased the area by a factor of 1,000. And also we improved all our processes, which then allows us to increase the speed of the fabrication. But this is of course not where we want to stop. We now, since then, also have a joint development agreement with one of the largest machine producers of the semiconductor industry. It's one of the biggest glass producers globally as well. And we are working together to scale the production of these batteries. And this summer, we have been the first time in California in one of the research labs where we showed that we can fabricate our batteries on their industrial-sized machines. And here you can see Abi holding one of these large cells, which is 300 times 300 millimeter in size. And this is really the largest what we have fabricated today. And we will continue to scale this, and we're already looking at larger machines and currently in the process of ordering the materials to produce on even larger scales this winter. And here you can see how such a cell performs today. Here you can see the capacity of our cells. So we are already in a regime of above 1 milliampere hour, which might not seem a lot to people coming from bulk batteries. Coming from thin film batteries, this is a huge step forward going in this direction, because typically we are speaking of a few microamp hours. So we already have milliampere hours, and we can show that we can also cycle them for a very long time and at fast C rates. So you see different C rates, and on the right you see the cycling performance of one of these cells. If we cycle this at 20 C, both charge and discharge, meaning just 3 minutes charging, 3 minutes discharging. And this over several hundred cycles. In this case, we showed above 500 cycles. And this is something which is already not easily possible with classical lithium-ion batteries, but also not with solid-state batteries. We also showed the fast charging characteristics of our batteries on the left. You see what happens if we charge these batteries in just 1 minute. So what we do here effectively is we apply a constant voltage and to charge the battery for 1 minute. And if we do this, we get 40% of the capacity out again. So we can charge 40% of the battery, full depth of discharge in just 1 minute. And if we go to 5 minutes, we're already above 80% of full charge of this battery. This is and we know exactly where to work on to improve this even further. We also showed that we can get very high power peaks out of these cells. So here on the right, one customer which we're talking to, he is using cells to send signals using LoRaWAN. LoRaWAN is a sending protocol which usually needs power peaks of 60 milliamps. So often there's a capacitor used for that in combination with a battery. And here we demonstrated that with a cell, which had just a bit less than 2 milliamp per hour, we could still deliver this high peak current of up to 60 milliamp, which would make it feasible to send signals via LoRaWAN. So where do we want to use these batteries? We have several different markets which we're currently looking at, whereas the entry market is clearly the wireless sensor market. The wireless sensor market is a market where often you have, for example, a small battery and a capacity together to power an application. You measure some signal. This can be, for example, humidity. This can be temperature, and then you store this this value with a battery, but you still need high power peaks to send the signals. So this is one application we're looking at, and especially I can show you here. This is one of our prototypes. We are now working on building a battery which is very thin, just 0.1 millimeter thin, to be integrated into applications like a credit card, where you can add a biometric fingerprint reader, or something like an ID card as well, where you could also add a biometric feature or other features into the devices. And we see that there are many companies now looking at these type of applications for cards, but also for labels. This can be, for example, electronic shelf labels in supermarkets as well. We're also looking at wireless sensors and hot temperatures, because our battery can handle higher temperatures than typical today's batteries. There are some use cases where wireless sensors again are used in industrial settings. For example, measuring the frequency of some motors for predictive maintenance. We're also looking in different sectors, for example, the medical sector. Here it's really important that the batteries are safe and have a flexible form factor, that you can really adapt them to the applications you're using. Our batteries are from the shape are very customizable. So we are looking along as well in this sector a lot. And consumer electronics, of course, which is especially interesting for fast charging. For example, you can imagine your portable earphones. If they run out of energy, you typically have to put them into a box to recharge them, and this still takes quite a while. If you could charge in just 1 minute, this would be of course fantastic, and this is also a market which we're looking at. We have contacts in all of these three markets today. We are talking to many companies for pilot projects. We have one pilot project already in place, and we have sold the first batteries this summer. Now, I want to also share you a bit about the story. How did it come how did we come to the point where we are today? So the idea of the startup started really in 2021, where I was a postdoc at Empa, and I was in contact with a lot of industry for potential new research projects. And there I already saw that there's a big interest for the technology which we're developing. But I also saw in the lab that technology is already working quite well compared to some other technologies. So, for example, comparing, we can build full solid-state batteries, and we can even deliver them without any encapsulation, and they still work. So it started around that time when a company actually asked us in one of the meetings why we are seeking funding from somewhere else, and why do we seek for partnerships? Why don't we start our own company and develop this further? And this led to a lot of thinking and an academic approach first, where we tried to understand everything, what it needs to start a company, what it needs to start a spin-off in Switzerland. And took a while until we hired the first person to build this proof of concept. And this is what the publication I showed you, with the stacking several cells on top, 2 cells on top of each other. We filed a patent, but also submitted submitted the publication. In parallel, we got initial coaching by InnoSwiss. So Bettina, who was on the first slide, is our InnoSwiss coach who helped us to formulate a business plan, but also a financial plan to start our company. And then it was initially somewhat of a side project still, where we worked on it, but we also had a lot of other projects to work on it. And then it really started in beginning of 2023, where we got funding from the European Space Agency and especially the business incubator of the European Space Agency. This also forced us to incorporate the company. So we incorporated the company in April of last year as a spin-off of Empa. And since then, the pace really, the speed is much faster, and we are growing a lot, and we are scaling a lot, especially. And here you see what happened since then. We quickly after have also become a spin-off of ETH Zurich, and have support from all other partners such as InnoSwiss Core Coaching, Bridge Proof of Concept, but also Battery Foundation. And we also got some funding, dilutive funding, in this case, venture kick. And only 8 months after we incorporated the company, we also had some pre-seed. We closed our pre-seed investment round, in this case with Hightech Gründerfonds, which is a venture capitalist company within Germany, and together with Zürcher Kantonalbank, which really helped us to focus on this more intensively and to bring this further. And this allowed us to build the first MVP of this cell, the characteristics I actually showed you, which allowed us to sell the first batteries to a first customer, and also to secure a first pilot project, which actually has started just on Monday. Now, what are our plans for the future? So today we are roughly at TRL 5. And our aim is to be on mass production and TRL 9 within the next 3 to 4 years. What we are doing today is we are still building this minimal viable products. At the moment, we're using facilities which are available at Empa. But at the same time, we're also working on scaling our production. And here we're working together with a machine producing company using within our joint development agreement. We have done the first production tests, which I showed you a picture of, and we will have further production tests this winter, with the aim to use one of these machines as a pilot production. This pilot production will still be on a rented machine, and then really only in about 2027, we plan to have the first series production ourselves, to be able to produce a large number of this very thin batteries, which will be integrated into credit cards. And once they are on the market, these will be actually the thinnest solid-state batteries, or the thinnest batteries in general, which we will be able to find on the market. This is all I wanted to share for today. Thank you again for having me and for also listening to the talk, and I'm looking forward to any questions you might have.
Yeah, thank you very much, Moritz, for the very interesting insights and to battery. We still have time for some questions here in the audience. So please raise your hands so that I can allow you the microphone and that you can ask directly questions or write the questions in the chat as usual. Here we have one. Well, the microphone is open. Please introduce yourself quickly. Can't see the name. Yes, who is it that raised the hand? Your microphone is open. You're still muted. Otherwise, please write it in the chat quickly if there is a problem with opening your microphone. Anyway, maybe meanwhile, well, you mentioned this partnership, right? That helps you at least on some of the machinery. But yeah, can you say a bit a few words about how you want to scale the technology and how much time, I guess money, that's not reasonable, but what do you think? And do you have already some target prices? I guess it will be different from standard lithium-ion battery prices because it's for different markets. But
So for the scaling of the production, we really here work together with a machine producing company. We already have the first concepts of what a series production would look like. And now it's really the final tests within the next round to test all of these parameters, which is needed to really be sure what a production will be looking like. We aim to have this in Europe, continent Europe, so also Switzerland or somewhere else in Europe. Not quite clear yet where such a production should stand. Important for us is here, what is the electricity mix we want to have it as green as possible. And from the price wise, it will not be comparable to $1 per kilowatt hour. It's more in these smaller devices, it's more unit price. And this way we will also adapt the unit price similar to, for example, what you see in capacitors and small coin-side batteries.
so means also the battery will be somehow integrated in a housing like in semiconductors, that you can solder it to PCBs.
Yes, we're really looking into where we can integrate the battery directly. For example, in a card, you can imagine the card will be needed to be laminated. And the batteries can be laminated directly with the rest of the electronics. So we really want to have an integrated energy storage solution here.
Okay. Well, there's a question from Jakub. So from the picture with lithium-free anode, there was apparently quite a bit of cell breathing during lithium plating. Is this the case, and will it be a problem for large stacks?
Sorry, what was the large? I didn't. This one, right?
Yeah, he's talking about the cell breathing during the lithium plating.
Yes. Oh, of course, there will be always quite a lot of volume change in anode-free thin film batteries. But here again, this is a thin film battery, so the volume changes we're talking to is still in the order of micrometers, tens of micrometers maybe, and this can be most likely be captured by a packaging itself. So we don't see that as a big issue for us for these thin batteries. I see there's another question in the chat.
Yes, you can read it.
Yeah. So what is the size of the 1 milliampere hour battery you showed? The size in the order of several tens of square centimeter, roughly. And what is the layer number you've achieved up to now? Is that a question? So we showed that we could stack three cells on top of each other. That's what we showed. Right now, this is what we showed so far.
Okay. With also like what's the maximum voltage that you can achieve?
That very much depends on the cathode which we are using in the end. How much voltage we achieve, and this is actually an interesting problem which then faced that many cyclists are not made to have both very low voltage current resolution, but also high voltage high voltage range. So we're limited in a way with cyclists as well, which cyclists can do this. And we actually now not looking too much into producing cells with high voltages. Initially, we thought it's interesting to have a cell with a high voltage, but engaging with the market, we learned that capacity is much more of interest, and the voltages, standard voltages, typically what customers are looking for. So we're actually now working on increasing the capacity rather than the voltage.
Okay. Good. So we saw NMC 811, so I guess that gave us a hint. And there is another question from Nikhil. That's about that's the job offering, I guess. Also, do you accept undergraduate interns currently? That was a question from Nikhil.
Well, there is a intern position at the moment online, actually, on LinkedIn. So happy to look at it and apply.
You find it on the LinkedIn profile from Moritz. I just saw that before. Okay. Do we have something else? Yes, there is a question. Give me a sec. Well, now you should be able to speak. Yes.
Hello. Yes. Yes, I have a question. You showed in a graph where it's written potential of multi-cell thin film batteries depending on the loading of your cathode. You can reach up.
Oh, now we can't hear you anymore. Yeah.
Is it back? Is it?
Yes, now it's back.
Yeah.
Yeah,
Okay.
yeah.
Okay. So I was wondering if you have such high series solicitation, you might have also the risk of lithium plating still, right? Because you have these very thin layers. I know you have solid electrolyte, but
So I think the question was about the lithium plating. We lost her
sorry,
again.
Yeah, okay, so I'm back again. Yeah, so I was wondering if you explore these. So how many cycles you could well sustain at such high C rate without the plating?
Yeah. So first of all, we want lithium plating for the lithium metal anode side, of course. We don't want it on the cathode side. We have never observed this. There would be a lot of overpotentials needed to achieve this. But we've shown 60 C in short current pulses, but the longest what we did for cycling test is 20 C, what I showed you, and there we didn't observe anything like this. But this is still definitely something which we need to look out for if we observe this in the future or not.
Okay, thank you. So nothing like voltage drop from short circuit from cathode and anode side, right?
No, there we published some work as well on the, it's more on this work here, where we show where are the limits. And here what we learned is really that you have to work clean. And if the interface is clean between the solid electrolyte and the current collector, usually very high current densities are possible. And we don't easily observe a short. Of course, this now has to be true for a very large area to be clean and defect free there. So this is another challenge. But if we work clean, then we can achieve very high current densities for plating and stripping.
Okay, thank you.
Good. Then there is another question from Peter. And in terms of performance, your batteries are very promising. Do you consider issues of recycling of your batteries?
Yes.
Yeah, well, I guess it's not the same as like, large batteries, large battery packs in automotive, in e-bikes or applications like that, right? So
Yes, indeed, it's not the same, but it's still something which we're looking at, especially now talking to integrating this into devices. There always has to be already a plan how to recycle these in the end, because there will also be regulations how to recycle batteries and components into devices. And probably it will be very different than today's lithium-ion battery recycling. We have very briefly looked at it so far. We didn't have the time to focus on it, but there are concepts, for example, in solar cells. In solar cells, these are also very thin layers, solid layers stacked on top of each other, and there are methods to separate the layers from each other. And then you can really separate the materials. This is something which we would hope to do in the future, but we haven't had time to look at it in detail yet.
Then we have, I would say, we slowly head to the last question here. It's a very good round, but we have a question from Andrea, and is mentioning high energy density and high C rate. Do you expect to be cost competitive with respect of thin film battery and supercap? Or do you target application where miniaturization is key and the two other together battery supercap cannot make it?
So thanks for the question there. Cost price is definitely an important issue, and we are currently working on what will be price on mass production scale. We see that we will be very close to the price of other thin film batteries and also supercapacitors. So I think we will be able to reach in a very close price range there, and especially if it's an application which uses both a supercapacitor and a battery, that's even better. Then we should definitely be also able to be cheaper. But the main focus which we are now looking at is really at applications where there's almost no technical solution today. So, for example, directly laminating into a card in a thin form factor. There are primary batteries which can do this, but there's no secondary battery which can do this in this thin form factor. The thinnest which we've seen so far is 0.45 millimeters in thickness. And partly this is because they still use liquid electrolyte, so they have to use pouches, and pouches are very thick. And since we use all solid state methods, we don't even need to use pouches. We can look at other encapsulation methods to protect our layers and to be even thinner like this. So we really look at applications where there's no technical solutions today, which is much more interesting for us. But then in the future, of course, applications where small batteries and supercapacitors are used.
Mm-hmm. Yeah, so maybe an additional question from myself here. So are you also looking into like medical devices, or do you think this is like too challenging because of the lithium metal, or even like completely unachievable because of lithium metal, or do you have any idea on that?
We're looking at medical devices in different directions. At the moment, mainly medical devices out of body, and there this would not be an issue as far as I see. Of course, we didn't went through a whole certification process, so maybe there are some surprises in the way. But as far as I see that this is not a problem so far. And yeah, we're looking at it especially for the miniaturization and the flexible form factor. This can be quite interesting. And then also in some aspects, medical devices need to be sterilized, and then of course also hot temperatures are important.
Yep. Yeah, very interesting. I think I would have so many other questions, but yeah, I think we would stop here for today, and thank Moritz again for the interesting presentation, and wish you good luck with further development of the company, and see you all next year again on the Battery Tuesday starting February. Wish you Merry Christmas and Happy New Year, and looking forward to 2025.
Thank you again for having me.